Hello everyone, this is the start of a new series that we're doing here at Zadar where we talk about our technology and our philosophy on imaging radar. I'm David, I'm in charge of hardware here at Zadar Labs.
I'm Mazi, I'm the Chief Business Officer at Zadar Labs.
And I don't know, Mazi, why don't we just jump right in? What do we do here at Zadar?
Well, at Zadar we have the market's best 4D imaging radar. We have a lot of customers from different sectors of the market, surveillance, security, mobility, robotics, mining, agriculture, heavy machinery, all sorts of different customers. They all need 4D imaging radars because these radars are very robust in different weather conditions, different lighting conditions. Computationally, they are very inexpensive, and the cost is definitely less than LiDARs. And for some applications, there's just no other solution out there except for the radar.
Yeah, and one of the things that is key is our imaging radar technology has reached a level of performance where we're starting to unlock these new applications and new solutions that can kind of, before our customers really thought that these problems that we're solving with radar, and we'll talk a bit more about the problems that we're solving, seem to be impossible. And now with the combination of radar's benefits and our performance that we deliver in our products like Z Prime and Z Pulse, our customers are developing robots for extreme conditions that have never been possible before. We're using radar to count people in situations where it's been very, very difficult to count people before, and we're bringing safety to machines in these very high stakes and very rugged environments like mines, like ports, things like that.
Yeah, maybe you could touch on the last customer experience you had where radar was deployed in a port. What was that experience like? What was missing from the existing sensors, and how did your guys solve the problem?
Yeah, so we recently had a customer deployment in a port for collision warning around heavy equipment. And there's a lot of very, very specific equipment that's used in the port environment to move containers around.
You could name the machine.
Oh yeah, it's called a straddle carrier.
There you go.
Which is this huge, tall machine, and the driver has very limited visibility around the edges of the straddle carrier.
Yeah.
And ports are these environments where you've got humidity, you've got salt water, you've got fog, you've got rain, and because of today's sort of high pressure port environment, they're running operations on these straddle carriers 24/7, at night, during the day, during weather, and sort of operator accidents and downtime in general in the port environment is something that's critical to eliminate. And existing collision warning systems used optical sensors like cameras and flash LiDAR, where in the actual deployed operation, dust and dirt on the lens detection misses, and also we found false alarms are a significant issue for the driver, because if you're driving this thing and it could be in the middle of the night, if you're missing things, that just kind of brings you a lack of security when you're driving.
Yeah, and as you said, false alarms are a very big problem because we noticed some of these operators actually stop using the existing system to turn it off because there's just too many false alarms, and it renders the system totally useless. We also noticed that the long-term maintenance cost is humongous because you have to, every other day or every few days, you have to have a crew go around and clean the lenses of these optical sensors. Again, optical sensors are great sensors, but in certain applications, you just have to spend a fortune trying to maintain the system operational. Well, we termed the first we termed our radar the first LiDAR quality radar.
Yes.
we claim that our 4D imaging radar, especially our flagship Z Prime, is the first radar that compares in performance to a LiDAR. How do you think we did that? Like, what enabled us to actually get close to the performance of a LiDAR?
Yeah, so this kind of goes and touches across our entire engineering philosophy at Zadar, where performance for us, and especially performance in the customer's application is key. And a big, huge metric here is angular resolution and the point cloud density of the radar itself. And kind of our philosophy here at Zadar is we need to consider the system as a whole and make optimizations across the stack, all the way from the silicon to the software. And this is where we found where we can get the most system level gains, basically, by co-developing the antennas, the antenna array with our signal processing, very unique signal processing stack, with our hardware, our manufacturing, and all of this designed specifically towards today's applications, applications where customers are using the radar point cloud and feeding it directly into deep learning, machine learning models for end-to-end actuation, where they're taking the point cloud and they're doing maybe raw processing or very, next level, next gen things for robotics using, transformers and all this sort of, new technology. We're kind of moving away from legacy radar in the way that in legacy metrics, where traditional, let's say, automotive radar has been designed towards, and developing a product that's targeted towards today's modern software and modern robotics autonomy stack.
Okay, thanks. In 2019, we invented the term software-defined imaging radar, and it is our trademark today. What do you think software-defined imaging radar is doing that previous legacy radars weren't doing?
So part of the concept of software-defined imaging radar is being able to modify radar parameters and modify radar performance based on dynamic needs of the sensor, and so, depending on the different applications where we might use a sensor, the same hardware platform can be used to detect, let's say, trucks all the way up to 1,000 meters for highway driving or for traffic monitoring. That same sensor can now also detect at a very high resolution and a closer range, let's say, image-like qualities in people walking around just in front of the sensor. And having this software-defined philosophy allows us to take one or two shared hardware platforms and squeeze the most performance out of it possible for every potential use case, to optimize our sensor for every customer that comes our way, because every application we see from every customer is frankly unique.
Yeah, it is. We have customers that want to literally detect nuts and bolts on an airport tarmac. We have customers that want to detect like potholes on the surface of moon. We actually literally had a customer that that wanted our Z Prime to detect unevenness on the surface of the moon. And some customers want ranges up to like 10 meters, some 5 meters. Some customers want a couple of kilometers. So we got all sorts of different needs for the software-defined imaging platform that we have. And we could easily change parameters, as you said, and the same platform, hardware platform, could meet all these needs without developing a new hardware. So,
yeah, and part of what can enable that is our very unique processing stack that we've developed across all of our products, where maybe before you have these fixed parameters and your processing chain, your legacy processing chain, only has, maybe might only support a short-range mode and a long-range mode, or parking mode, for example. But the way we've architected our entire software stack, from the signal processing through the different software layers that we have, allows us to reconfigure and optimize and squeeze the most out of the hardware, well beyond what you could normally get.
So another question that comes up all the time when I talk to customers is that the customers compare a radar against LiDAR or cameras, and one big aspect of it is a computational complexity of the data that comes out of the radar versus the camera and LiDAR. How do you compare the point cloud of a radar versus that of a LiDAR, or the pixels of a camera, and how a computer, be it a CPU or a GPU or a Raspberry Pi, could handle that data? How do they compare against each other? How easy is to use radar? And holistically, when we talk about the cost, which is the cost of the sensor and the computer that analyze the data or process the data, how does that cost compare between these three different sensors: camera, LiDAR, and radar?
Yeah, Mazi. So the key difference between cameras and LiDAR and radar is that cameras and LiDAR are what we call dense sensors, where every pixel or every angle has some sort of information associated with it, whether or not it's relevant to your application. And the difference with radar is that radar is a sparse sensor, and radar only picks up on the most relevant information in the scene.
Maybe we call it attention-based sensor.
Correct, exactly. Radar will report to you what's most worth paying attention to. And another key difference of radar is that it's not a 2D sensor like camera. It's not a 3D sensor like LiDAR. It has 4, maybe even 5 dimensions, depending on how you want to count the data. Moving objects, dynamic objects in the scene will instantly pop out because we have Doppler information. And so for algorithms and algorithmic complexity that for systems that use radar, the information density and the value of each return that you get from radar is that much higher. And of course, there's a whole series, slew of new approaches you could take once you have that level of information density.
Right. A lot of customers ask us whether our 4D imaging radar actually detects static objects. Our answer is, well, it does. It's an imaging radar, so it detects both static and dynamic objects, but it detects the dynamic objects so much better because they're moving, and because of the diversity of the angles in a motion, a lot more points are returned back to the sensor. And as you said, in many applications, we could do static dynamic segmentations and throw away all the static points and just keep the dynamic points. Or the opposite, if you want to do SLAM or 3D mapping, you don't care about dynamic points. In fact, those are noise to you. So you want to throw away all the dynamic points, and that's so easily done using the radar with very low computational complexity. So what are the computational platforms that people could use to get the data and process? Like, name a few available platforms that people could use to receive data from our sensors, and also touch on the idea that these sensors have their own computer inside and could actually output the object list without really needing an external computer.
Yeah, so our radars are designed to be totally platform agnostic. Mm-hmm. The communications interface is standardized. It's automotive Ethernet or it's PoE, and we have example drivers for all types of platforms, whether you're on x86, Windows or Linux, or if you're on ARM, for NVIDIA platforms like Jetson or Thor or NVIDIA Drive. We offer software integration and drivers for pretty much every platform under the sun. And on top of this, for applications that are I want to say like a little more embedded, where there might not be a centralized processor. So let's say instead of a robot, now you're on like a tractor, for example. The radar itself has sufficient computing power inside to even do some of these higher level perception tasks. So that the radar can act as just an edge sensor that produces an excellent point cloud, or we can add on higher level processing within the radar itself. We can cluster the points for you, do tracking. We can do radar-based odometry to tell you, what kind of movement your platform is having using radar data alone without needing GPS or anything like that. This is all done inside the sensor.
Let's say someone wants to do classification. They define, let's say, 10 different objects to classify. How do you do that on the edge?
So we are able to take our radar-based classification algorithms and basically deploy those directly into the processor inside the sensor. If the customer, let's say, needs to classify some unique classes that we haven't seen before, we're able to, our engineering team is able to work with the customer to define, like a data set that has these different classes, to label it and train our own classification algorithm to run inside the radar to detect these classes. And we already have classification on the edge deployed in many different applications. We find the biggest demand for this to be in the traffic monitoring segment, where you might want to classify pedestrians against bicycles, motorbikes, trucks, vehicles like passenger cars, and based on that information, decide intelligently how you should, manage your highway, how you should manage your intersection, things like that.
I often get this question from customers that want to use our radar and train their own models to classify for different things. The customer can look at our point cloud very easily and train their models. That they understand. How do they move their trained model and parameters into our firmware and do the computation at the edge? What's the complexity of that? What does it take for them to achieve that?
Right, so if the customer already has a model that's, say, running on their development platform, and in the final application, they may not have this development platform deployed, they might want to deploy just the radar, that's something that we can support. And what our team can do is we can work directly with the customer to take their model, to take their architecture, maybe make some small tweaks to it to better suit the processing we have available inside Z Prime, and deploy that as a custom firmware and custom mode that the radar can then run and do classification on at the edge.
Right. And the advantage for them would be they don't need an extra computer. And they could save costs, and it's more elegant. It's less chance for failure.
Exactly.
Yeah.
Simplify the solution and push everything to the edge. Yeah.
Yeah, absolutely. So the other question, we have one application. This specific customer came to us. They tried all sorts of different sensors like thermal, optical, LiDAR. They wanted to count the number of occupants inside the vehicle at a certain checkpoint, and they wanted to do it with a very high accuracy. How does this solution work with the radar?
So one of the very unique things about radar is that radar can detect, motion of objects with very, very fine resolution. And radar doesn't necessarily need a direct line of sight to measure this motion, to measure these objects. And so one of the great strengths of our radar is that we're able to take, this high resolution radar that can kind of, see through glass, can see behind fabric, and see through objects to a certain extent. And we can set up multiple of these radars and synchronize them all in, let's say, the customer's people counting environment. And as vehicles drive through this like tunnel of radars, I think we deployed 3 or 4 radars for this application. The radars are actively measuring the location and the shape and the position of the vehicle, the velocity of the vehicle, and the radars can then remove the vehicle from the final point cloud, from the final data, and then we can look at just the moving objects inside the vehicle. And even very fine movement, just like normal breathing and like heartbeats can be detected by the radar, and we can count the number of unique occupants within the vehicle with a very, very high accuracy.
And localize them accurately. Exactly.
Localize them, exactly.
The other application is in agriculture. As you know, we have one customer that really tried hard to measure how the specific bin is filled with grain when this very high speed spout is dropping the grain, and there's a lot of dust in the environment. It occluded the lens of the camera, and the LiDAR was not working because, again, there's a lot of dust. How did we manage that specific application?
Yeah, so that was one of our end-to-end solutions. So, on top of providing a fantastic sort of imaging radar platform for everyone to just take our radars and use as raw sensors, we also develop full end-to-end solutions using our technology for customers, using Z Prime, Z Pulse, all of our imaging radars, plus like a computational ECU, for example. And in this case, for this customer, we implemented a full end-to-end fully automated robotic system that uses radar to accurately fill these bins to the correct level. And not just with like a fixed bin location and a fixed spout, but these bins in this application are moving around, and the radar will detect the outline, shape, and location of the bin, how full the bin is from the base level to the top, and our system will then end-to-end point the filling spout to where the bin is, fill the bin to the correct level, and also make sure that the bin is evenly filled from end to end. And this bin is 40 feet plus long. So we're tracking the location of the bin, we're tracking the location of the spout, we're aware of exactly the level where the grain is everywhere inside the bin using just one Z Prime radar. Yeah. And it's a testament to the high detection accuracy and performance of the radar in order to be able to do this in such a dirty, dusty environment.
Right, and it does it faster and better than the human operator.
Yes, with less grain spilled and faster cycle times.
Right. If you remember, a few years ago, we had one customer with one application. The application was they had these massive buckets that were digging into the mountain, and they wanted to find out if the teeth of these buckets have fallen down, or if the teeth are eroding, because if these buckets are down for even an hour, the loss for the mine is very massive. How do you think our Z Prime did that?
So we, for that application, really leveraged the SDIR, or software-defined imaging radar, capability of Z Prime. There we were able to deploy custom detection algorithms, custom beamforming algorithms that really were able to get extremely high spatial resolution in the area of where these teeth were with the same hardware platform that we deployed to everyone else. And as these teeth were eroding, we could measure with centimeter, millimeter level accuracy how much metal was being removed from the tooth with every scrape of the bucket, or if the tooth suddenly fell off the bucket, which was actually the critical case that this customer wanted to detect, we could detect as soon as that tooth fell off the bucket. And when that tooth departs the bucket, if that tooth makes its way, that steel tooth makes its way into like the crushing, grinding equipment, that shuts down your whole mine. It could be millions of dollars per day of downtime.
Right.
Sorry, can you come a little forward on the mark there?
You understand what I'm talking about?
Yeah. Well,
self-driving automotive? AMR?
Yeah. So the other application that we get is AMRs, or robots, or delivery robots. People want to put radars around these smaller vehicles that move around. What offerings do we have that distinguishes us from others in the market when it comes to AMRs?
Yeah, so for smaller platforms like AMRs, like indoor robots and such, we have a number of very compact and high-resolution radar platforms that we can deploy for these customers. And again, these smaller platforms have all the same processing DNA that we use in our high-end sensors, and have all of the same SDR capabilities that are in our high-end sensors, are found in our high-end sensors. And this lets our customers deploy AMRs in applications that are quite a bit different than traditional automotive, where they're still using radars for detecting obstacles and incoming objects and navigate the environment. But our radars are also have high enough spatial resolution to provide things like free path, to detect where this AMR can go, to detect very fine objects that you might see on a sidewalk that most cars don't have to worry about. For example, very thin wire fences where LiDAR and camera struggle to detect these like visually very small objects. To the radar, this is like as clear as day. And also, there are other critical scenarios that AMRs have where vehicles may not experience, like let's say a bicyclist wearing dark clothes approaching the robot late at night, where you may only get a few points from your LiDAR, you may not get any classification at all from your camera. In that situation, the radar will detect that as clear as day.
Yeah. And the latency is really important here. No other sensor comes close to the latency of a radar.
Correct. Yeah. So one of the things that we really focus on, again, is the full end-to-end suitability of our radars for robotics. And in our case, we offer frame times of 50 milliseconds, 33 milliseconds, 25 milliseconds. So this is like 20 hertz, 30 hertz, 40 hertz that we're getting out of our sensors. So for lightning fast reaction times. Yeah, we're really well suited.
Every, let's say, 25 milliseconds, the points in the point cloud have the velocity information in them. So you don't have to extrapolate like you have to do for a camera or a LiDAR. It's right there available.
Exactly. Yeah. Instantaneous velocity, every single frame.
Yeah.
Yes.
Yeah. What other thing we've noticed is that a lot of these robotic customers like the fact that these radars could be actually hidden behind the surfaces or the fascia. And they won't be, subject to tampering by people or weather conditions. Mm-hmm. That's also a big benefit.
Right. Because of the wavelength of the radar that we develop, 77 gigahertz has a wavelength of around 3 millimeters. This means that our imaging radar technology is inherently resistant against raindrops, against dust, against particles in the air, against even like falling snow, fog, stuff that would blind or otherwise confuse an optical sensor. And because of the wavelength of the radar, and because radar can penetrate through transparent materials like plastic, for example, you can hide radar behind fascia, have it be fully seamless, hide it behind walls, behind any kind of surface, and then which is fantastic for let's say the industrial design teams out there that want to make sleeker and more beautiful looking robots every day.
Yeah, and the radar is a great sensor to preserve privacy of people, because it doesn't identify a person, because it doesn't see colors. It knows it's a person, but it doesn't know who the person is. So that's a very important aspect of using radars for indoor application. What offerings do we have for indoor applications where people are looking for, people counting fall detection, breathing rate, heart rate monitoring, all sorts of activity monitorings? You could name the product that we have, or what technology we use, and how is it different from the technology that is deployed for, like, let's say, mobility.
Mm-hmm. Yeah, so we're taking our mobility-based solutions and technology and applying it to a new frequency. This is 60 gigahertz, specifically 57 to 64 gigahertz.
How much bandwidth do we have there?
We have a good 7 to 8 gigahertz of bandwidth, depending on the country.
Unlicensed.
Unlicensed, yes. Which means that for indoor applications, we can take all of the same high-resolution, privacy-preserving point cloud information, high-density information, and now look at activity of people indoors, maybe in a highly secure environment where you may not want to know who's coming in or out, but for security reasons, you may need to know if there are people in a room, for example,
or restrooms or fitting rooms,
or like hospitals, for example. The high-resolution, high-performance point cloud that we get from our technology can be used to determine when, let's say, someone has fallen in a hospital room and they can't get up and they can't reach the alarm, for example. And also with radar technology these days, the Doppler sensitivity is fine enough that we can even detect vital signs like breathing and heart rate for, let's say, elderly care and other situations like consumer electronics, treadmills, for example.
Or infants.
Exactly.
Yeah. So at Zadar, we have the world's best 4D imaging radar. We serve many markets: surveillance, security, robotics, mining, agriculture, and more. We would like to hear from you. We want to know what your application is, and our team is more than happy to get on a call with you and discuss potential partnerships, and we would be happy to serve you.
I just want to say, thanks, Mazi, for opening the discussion today on what makes Zadar unique, on the different markets that we're serving, and how we're taking this legacy imaging radar technology and bringing it to the future.
Thank you so much. This wouldn't all be possible without great work that you and your team is putting into this. Thank you so much.